So this particular topic that I'll be speaking today is based on the work that we just finished, and we are going to submit it soon. But of course, those are the follow-up of a series of work that I have worked on with my several students, and out of them, Ayon already he has spoken, and Subhasis already has spoken, and today Reajul, I don't know whether he is here or not, but he will be speaking today. Okay, so before I start, let me give you the basic message that I wanted to convey through this talk is the following, that if we assume dark matters to be particle-like, then if there exists inflation in the standard model of cosmology, then this inflation will produce large-scale fluctuations, which is part of the title of my talk. And then that large-scale fluctuation is going to affect significantly the dark matter phenomenology. Or in other words, if I want to make it a little more ambitious, then the statement that I want to convey is that the conventional phenomenological approach may not capture the complete picture of the dark matter physics if standard model cosmology includes inflation. So this is what the message that that I want to convey through this talk. Okay, so part of the reason that why the usual phenomenological approach to dark matter physics cannot capture the physics of dark matter is maybe one of the reasons could be this question that typically they don't ask is how does the present state of our universe arises? So this is the question that typically they don't ask. And with this slide, I am also taking this opportunity to say a few words. The present state of our universe certainly includes my campus as well, and this is the campus where we live and where we write papers. And there are several things. One thing that I should mention is these hills where Kamakha temple resides. So if you are interested in history as well as Indian culture, certainly you can visit. And of course, if you want to visit us, you can write to me, and then we will be happy to host you. Okay, coming back to the question, how does the present state of our universe arises? And what I want to emphasize is that inflation is the one which actually gives rise to this initial condition. So if inflation happens, and if inflation is part of the standard model cosmology, which is, we believe that the large number of cosmological observations already make us believe that yes, inflation could happen, then our inflation will have generically two phases. One is of course cold phase, and that is driven by inflation, and the another one is the hot phase, which is after that is coming, which is the standard Big Bang that we know. So of course I am not particularly interested in describing what is inflation and what is in hot phase. And another point that I would like to mention, that standard model particle phenomenologies that do talk about physics of dark matter, they always begins with this assumption that there is a hot universe, and from there you start building up your model of standard model of dark matter. So in this talk, I will not be talking about inflation. I will not be talking about this hot Big Bang, but I will be talking about the phases, the phenomena that happens in between these two lines. Okay, and there are many questions that you can ask regarding this transition from inflation to hot Big Bang. Out of this, I will be mostly my concentration will be on this question: what role does inflation play on the dark matter physics, and then the follow-up questions related to the gravitational wave. Okay, so let me go a little more detail. So if inflation happens, then at the present time, what we expect, or what you see, of course, is just the background, and on top of that fluctuation. These are the one that you have been hearing over the last 3-4 days. So after the inflation, many things happen, and then finally what we observe is background and fluctuation. Backgrounds, what is the background, what are the fluctuations, I don't need to explain. And the main mechanism through which this transition happens is basically the quantum particle productions. So that is what the main mechanism by which you can obtain the inflation to the hot Big Bang and the present state of the universe. And such production mechanism will be driven by two classes of uh, interaction. One is through non-gravitational, which is basically you construct your models of inflation coupled with all the standard model particle, and then you try to understand how this inflate and decay. And another one, which is the purely gravitational one, and which is universal in the sense that you cannot avoid having this. It is basically there, already there, even though you don't have any coupling of the any field with the inflaton, but simply because gravity is there, so gravity will give you particle productions from the inflaton as well, moment you have time dependent background. I will be particularly focusing on this particular phenomena where particularly the dark matter physics, which will be produced by inflation purely through gravitational interaction. There is no interaction with the inflaton field. Okay, so what is inflationary particle production? It is extremely simple. It is the same as the one that you already know in the Swinger mechanism. So what it does, if you have a constant background electric field, then a virtual pair of electron positron will feel a force, and because of that force they will gain energy. And then if the energy of the electron or positron gain the energy which is compared to the energy of this rest mass energy of the particle within the Compton wavelength of the electron, then you can create a virtual pair to real pair. Basically, that is how the pair production happens in Swinger mechanism. So here exactly similar type of things happen in inflationary background. But for this case, you don't need to have the charged particle. It can happen also for any neutral pair as well. So if you have a neutral pair, virtual pair, then if you have background expansion, which is exponentially expanding, then you can have a possibility that this virtual pair can gain a velocity which is close to velocity of light because of the expansion within the within the Compton wavelength of that particle. Then naturally that will give rise to real particle out of virtual particle. So this is what exactly happens in, but it is not, even though it is a simple-minded picture, but if you want to do the real calculation, then what you have to do, you have to solve your field equations in this inflationary background. Okay, so now what you do, let us assume that I have a scalar field which I assume to be a dark matter, massive dark matter. Then if you calculate the mode function of that scalar field in this background, typically you have this kind of equation, where this is my time dependent frequency. Now you can see here the universe is expanding, so that is why the background is time dependent, and because of the time dependence your particle production typically will happen. Okay, the nice property of this inflationary background is that, as I said, that because there is a background time dependence, it is very difficult. You cannot define what is particle, because because there is no time like killing vector. You cannot define the appropriate definition of the particle. So that is why you have to have some limit where you can interpret your identify or define the particle. So a nice feature of this inflationary background on this particular background is that this frequency has a nice property. If you take very small wavelength in this limit, meaning if you go eta goes to negative infinity limit, then all these modes will be deep inside the horizon, and they will not see the overall curvature of the space-time, and that how this particular feature can give you a handle that you can define a vacuum which is typically called adiabatic vacuum, where your frequency varies very slowly. That is called adiabatic vacuum, and you know this vacuum is known as this Barnes-Davis. So that means I can define a adiabatic vacuum for all those modes which are deep inside the horizon, and I can expand my field mode with respect to those modes which forms a complete Hilbert space. Similarly, same field can also be different. There exists another adiabatic vacuum in the far future, where also this omega will vary very slowly, and you can define another adiabatic vacuum when those modes are inside, deep inside the horizon, and there also I can define a vacuum where your fields, this omega varies very slowly, and then you can. So that means the same field can be expressed in terms of these modes in far past, and same field can be expanded in terms of these modes in the far future, where you can identify particle. You have the particle interpretation. And now you know this, if there is two vacuum here, the same field can be expanded in two different Hilbert space, then you can always relate this to Hilbert space by Bogoliubov transformation. That is the standard technique that you do in quantum field theory and even quantum mechanics. And that is how precisely identify the particle number density. And that particle number density is actually related to this beta and the standard notation. So if you have seen it before, then you can easily identify. And this alpha are basically the Bogoliubov coefficients, and they satisfy this SU11 relation. And then I identify beta to be my particle number density, co-moving number density. Remember that when I'm saying these are the particle, this is valid only when those modes are inside the horizon. This is very important. Okay, so now let us try to give you some typical form of this spectrum beta. But before that, let me just make few comments. So if you take in inflationary background, if you consider massless fermion and vector boson, then because of this conformal invariance, those particles cannot be produced. So this is a typical property of conformal invariance. But of course, any massless scalar field or any massive fields can always be produced through this mechanism, this inflationary time dependent background. And of course, you will see here today another talk by Raghuvir, who will be talking about how to break this conformal invariance by taking into account the perturbation. You will see how there also you can produce the particle. Okay, so coming back to my beta. So typical form of the beta spectrum will look like this, a power law, and then there will be a complicated function of again E, which is a function of K, mass, and the energy scale in which you are talking about this. And you can see that this kind of form already you have seen, which is related to your structure form, really the CMB fluctuations. Actually, this is exactly the same mechanism by which you consider the curvature fluctuations. Here also I do the same thing. I assume a scalar field, and then I do the expansion and try to figure out what is the spectrum corresponding to the scalar field, what you do or usually for the inflaton fluctuation. And I will be mostly focused on this infrared meanings which are greater than the scale which enters at the end of inflation. So that is why you call infrared. And all the modes that are within the Hubble horizon, inside the Hubble horizon, the later stage of the universe, we call it just ultraviolet. We will not talk about this, because typically what happens, all the modes which are inside the horizon has a suppression. Of course, this part of the scaling is not pretty generic, depending on what kind of reheating mechanism you are talking. But since this is highly suppressed, I will be only focusing on the modes which are outside the horizon. Okay. Okay. So now, if I assume this number density to be the number density of particles, dark matter particles, then how those dark matter will contribute to the phenomenology that we are talking about. Two possibilities. One is dark matter being completely dark, meaning that there is no interaction with anything. It is just purely dark matter, and only interaction that it has is the gravitational one. So that's why I call it completely dark. And another possibility that is there, which is related to the phenomenology that I was talking about, if this dark matter interacts with the standard model fermion, then how does this phenomenology of dark matter that usually people do alters because of these large scale modes. Okay, so this is dark matter being completely dark, meaning, so these modes are entering into the exiting the horizon, and these are the modes that I was talking about. These are all the modes which are essentially infrared modes, and they will enter subsequently in the subsequent evolution, and they will contribute to the total dark matter density that we have today. Okay, so what you do, you just calculate at the present time what is the total number density, and then you multiply their mass and you will get the dark matter abundance. And this is how, because it doesn't interact with anything except the gravitational interaction. So what you will have, it just freely propagate and then contribute to the total dark matter content of the universe. And you can compute what would be the mass if I take into account solely those infrared modes. And this is how the mass versus delta relation appears. So you have only one parameter. Of course, I introduce this delta to be another parameter. I assume this delta, typically if you fix a particular model, then delta will be fixed. But for the time being, for our analysis, I just assume that delta to be arbitrary. Okay, so if you assume this delta, vary this delta and mass, then typically, and this is the completely gravitational dark matter, meaning there is no interaction with the gravity, then these infrared modes are completely responsible for the present dark matter abundance. You can have a huge parameter space where these infrared modes will contribute to total dark matter that you have at the present time. Now we can go to next situation where my dark matter is no longer gravitational. All the dark matter phenomenology that people do, typically their starting point is this region, not in this region. So you have the thermal bath in this region, then from this thermal bath, you interact the dark matter with the standard model, and then you evolve. That is what usually they do. But now what you are doing, there is a dark matter infrared modes which will keep entering throughout this evolution. And that will contribute to this additional component, which is, I am saying, the infrared dark matter injection. So you have this traditional part which usually people talk about in the usual particle dark matter phenomenology, and we have this additional infrared injection coming from this long wavelength fluctuations. Okay, so let me show you what is the parameter space. That is so typically we have two possibilities. One is called a freeze in and another is called freeze out, depending on how you produce from the thermal bath. Okay, so and freeze in is essentially meaning that dark matter interaction with the thermal bath is so weak that it will never become equilibrated with the dark matter. And freeze out means it is initially is equilibrated with the standard model, and gradually because of the expansion it will become out of equilibrium. So these are the two possible mechanisms by which you can produce dark matter from the thermal bath, and these are the two possibilities, and you get these two possibilities out of this single equation. Okay, so this is the freeze in, meaning when dark matter are produced from the thermal bath, but dark matter are never in thermal equilibrium. They have a finite value of interaction with the standard model, but they are never in thermal equilibrium with the bath because of very weak interactions. So they can only be produced from the standard model annihilation. And this is the parameter space that you have. And then if it is freeze out, meaning which is the standard one, we will find that the huge parameter space open up. This line is essentially the standard WIMP miracle that everybody knows. Meaning, if I talk about simple particle phenomenological approach, means there is no infrared modes, only standard model particle, standard model of dark matter coming from the thermal bath. The only parameter space that exists in this simple model is this line. But now, moment you include, remember, this part contribution is completely universal, because this has to be there because it's just gravitationally produced. You cannot avoid having those. So if you include, then moment you include this, we have all this this huge region can naturally opens up without any additional physics. Without any additional, I am not introducing any additional physics. It's just simply, if you have inflation, this is the contribution that you have. Okay, and now if I put it in the experimental perspective, if you put all this data into freeze out and freeze in into the present context of with taking into account all the existing constants, then this is the part which is still available. If we think in terms of freeze out, and this is the part completely available, which if you consider the freeze in. Okay, so there is a huge parameters but still available which has not been explored. And then at the final piece of final slide is that So for every delta, this is the contribution. For every given delta, I have this parameter space, and that means, and because this delta is giving you a long wavelength fluctuation, that will contribute to the isocurvature. And we have also taken into account the isocurvature constants, and that is why I plotted the value which satisfies those isocurvature constants. And then because of the specific delta, and this will give you a long wavelength fluctuation, that can certainly give rise to a non-trivial secondary gravitational waves. And this is the predictions of the gravitational wave for different deltas, which actually you can see that they are naturally passing through various upcoming experiments. Of course, I cannot go further up because that will naturally violate the standard delta n effective bound and R constants. Okay, so with this, let me finish, and this is my conclusion and some future directions. I think let me not read it out, and thanks for your attention.
Okay, one or two quick questions. Oh, Shriram.
I presume the chi field is coupled to the inflaton in some manner, and
No coupling here.
how was the chi field produced?
Yeah, that is precisely is because you have this time-dependent background, and this time-dependent background
So
naturally.
it is just a chi field evolving in this background which is
Yes.
producing.
Yes.
Now, how do you know it's a dark matter particle? I don't know its
I
pressure.
just assume that as a dark matter. Yes, I just assume that. Okay, so the
I need to know the pressure density relation in order to claim that it is a collection of dark matter particles.
that is a good question. So that is the later part. So basically, what I'm saying that those dark matters. So these are the individual modes that will be produced during inflation, and they were never considered. But whatever people have considered in the usual phenomenology is whatever modes that is produced during this phase. So now what I'm doing, I'm just adding those modes that is coming from basically these modes. But those modes are already there before also in the usual phenomenological particle phenomenological model. Okay. I'm just saying there is an extra contribution coming from the inflation which were ignored before.
I agree. Yes. The mechanism, but yes. I think to claim that they are dark matter particles, we need to know the pressure.
Yes, we have to. Okay. Next thing is we have to calculate how this. So that is what.
Just one brief question.
Yes, yes.
You got a k minus 3 for beta k for k greater than ke somewhere.
K
so
minus.
Can you there on the right hand?
Yes. Yes.
Okay.
Yes.
Okay. But beta k square, k cubed is k minus 3. So beta k square is k minus 6.
Yes. Yes.
Okay, what kind of transition do you have?
So it is okay. I have taken this instantaneous transition. So from inflaton to directly radiation domination. If I include so if I include some other phase, then there will be a difference. Yes, in the spectrum.